Day 36, continuing the chapter 5 risk return and historical record. Let's begin. The equilibrium nominal rate of interest. Equation 5.2 tells us that the nominal rate of return on an asset is approximately equal to the real rate plus inflation. Because investors should be concerned with real returns, their increase in purchasing power, we would expect higher nominal interest rates when inflation is higher. The higher nominal rate is necessary to maintain the expected real return offered by an investment. Irving Fisher, 1930, argued that the nominal rate ought to increase 1 for 1 with expected inflation, EI, E1. This so-called Fisher hypothesis is nominal rate equals to real rate plus expected inflation. The Fisher hypothesis implies that when real rates are stable, changes in nominal rates ought to predict changes in inflation rates. This prediction has been debated and empirically investigated with mixed results. It is difficult to definitively test the hypothesis because the equilibrium real rate also changes unpredictably over time. Although the data does not strongly support the Fisher equation, nominal interest rates seem to predict inflation as well as alternative methods, in part because we are unable to forecast inflation well with any method. Um, Concept check 5.1. Suppose the real interest rate is 3% per year and expected rate is 8%. According to Fisher hypothesis, what is nominal? So R nominal will be equal to real plus expected. So real is 3, expected is 8, so that will become 11%. That's the nominal interest rate that the central bank will actually put in effect. Suppose the expected inflation rate rises to 10%, but the real rate is unchanged. What happens to the nominal interest rate? So our norm again, nominal rate will increase by 10%, so it will become 21%. Oh, rises to 10%. Oh, my bad. Yeah, 21% is the nominal. So let me just erase that. Okay. Rises to 10%, so it will increase by 2%, which will bring the nominal rate to 13%. So that was the concept check for 5.1. Taxes and real rate of interest. Tax liabilities are based on nominal income and tax rate determined by the investor's tax bracket. Congress recognized the resultant bracket creep when nominal income grows due to inflation and pushes taxpayers into higher brackets, and mandated index-linked tax brackets in the Tax Reform Act of 1986. However, index-linked tax brackets do not provide relief from the effect of inflation on the taxation of savings. Given a tax rate T and a nominal interest rate R norm, the after-tax rate is R norm 1 minus T. The real after-tax rate is approximately the after-tax nominal rate minus the inflation rate. Uh, okay. Didn't understand that. The after-tax interest rate is R norm 1 minus T. The real after-tax rate is approximately the after-tax nominal rate minus the inflation rate. Okay. Okay. Equation 5.5 tells us that because you pay taxes on even the portion of interest earnings that is merely compensation for inflation, your after-tax real return falls by the tax rate times the inflation rate. If, for example, you are in the 30% tax bracket and your investments provide a nominal return of 12%, while inflation runs at 8%, your before tax real rate is approximately 4%. Uh, yeah, okay. And you should, in an inflation protected tax system, net and after tax return of 4%. 1 minus zero point 0.3 into 1 minus zero point 0.3 into zero point 0.7, basically 2.8%. Okay, but the tax code does not recognize that the first 8% of your return is only compensation for inflation, not real income. Your after tax nominal return is 12% into 0.7, 8.4. So your after tax real interest rate is only 8.4 minus 8, 0.4%. As predicted by equation 5.5, your after tax real return has fallen by uh, 8% times 0.3, 0.24%. So I didn't understand that completely, but I think I got some of the idea of what it was saying. So, okay, let's move on. 5.2, comparing rates of return for different holding periods. Consider an investor who seeks a safe investment, say in the US Treasury securities. We observe zero coupon Treasury securities with several different maturities. Zero coupon bonds discussed more fully in chapter 14 are sold at a discount from par value and provide the entire return from the difference between the purchase price and the ultimate repayment of par value. Given the price PT of a treasury bond with $100 par value and maturity of T years, we calculate that the total risk-free return available for the horizon of T years as the percentage increase in the value of investment. Uh, what is this? Hmm. Given the price PT of a treasury bond with $100, tell you the total risk-free return available for T years. Percentage increase in the value of the investment. RFT. Okay. 100 by PT minus 1 price of a treasury bond. 100 by price minus 1. For T equals to 1, 5.6 risk rate investment price in a 1 year. Example 5.2. Annualized rate of return. Suppose prices of zero coupon treasuries with $100 face value, various maturities are as follows. We find the total return of each security by using equation 5.6. Uh, agree. Jesus, how did he do that, bro? Like, So I got distracted. Horizon T, price PT, 100 by price minus 1, total return for given horizon. Half year, price, okay. Then, okay. How is that connected to the horizon is what I'm asking. It's only connected to the price, no? I guess 25 years. Huh. 100, 100, 100. Okay. Yeah, okay. Sure. Not surprisingly, longer horizon and example 5.2 provide greater total results. Okay. How should we compare the returns on investments with different horizons? That this requires that we express each total return as a rate of return for a common period. Typically express all investment returns as an effective annual rate EAR, defined as the percentage increase in funds invested over a 1 year horizon. For 1 year investment, the EAR equals the total return, RF1, the gross return, 1 plus EAR, effective annual rate, is the terminal value of a $1 investment. For investments that last less than 1 year, we compound the per period return for a full year. For the 6-month bill in example 5.2, we combine we compound 2.71% half year return over two semi-annual periods to obtain a terminal value of 1.1 plus EAR, which is equal to 1.021 whole squared, which is equal to 1.0549, implying that effective annual rate is 5.49%. Second, okay, two semi-annual, 1 plus EAR. Huh. Okay. So it increased from 2.71 to 5.49 annually. For investments longer than a year, the convention is to express the EAR as the annual rate that would compound to the same value as the actual investment. For example, the investment in 25-year bond, example 5.2, grows by its maturity by a factor of 4.2918, that is 1 plus 3.2918. So its effective annual rate is found by solving. 1 plus effective annual rate whole to the power 25 equals to 4.2918. 1 plus effective annual rate equals to 1.0600. So therefore, yeah. Yeah, so therefore iska it's 6%. Okay. Therefore 6%. In general, we can relate EAR to total return, RFT, return total, over holding period length T by using the following equation. 1 plus EAR equals to 1 plus RFT to the power by T. We illustrate with an example. Example 5.3, effective annual rate versus total return. For the 6-month treasury in example 5.2, T equals to 1.2 and 1 by T equals to 2. Therefore, 1 plus EAR equals to 1.0271 squared equals to 1.0549, and EAR is equal to 5.49%. And like I said, it was 6% for the 25-year bond. So yeah, pretty good stuff. I understood this part pretty clearly, so that's good. Annual percentage rates, APRs, annualized rates on short-term investments by convention less than 1 year often are reported using simple rather than compound interests. These are called annual percentage rates or APRs. For example, the APR corresponding to a monthly rate such as that charged on a credit card is reported as 12 times the monthly rate. More generally, if there are n compounding periods in a year and the per period rate is RFT, then APR equals to N times RFT. Conversely, you can find the per period rate from the APR as RFT equals to APR by N, or equivalently as T times APR. Using this procedure, the APR of the 6-month bond in the example 5.2 with a 6-month rate of 2.71% is 2 times 2.71 equals to 5.42%. The generalized note for short-term investments of length t, these are n equals to 1 by t compounding periods in a year. Therefore, relationship among the compounding period, the EAR and the APR is 1 plus EAR equals to 1 plus total rate to the power n, which is 1 plus total rate to the power 1 by t, which is 1 plus t times APR to the power 1 by t. Equivalently, APR equals to 1 plus AR to the power t minus 1 divided by t. So let me understand this again, because I did not understand anything and I was just reading it like just casually. Short-term investments, T less money up, simple interest. Okay. APRs are less percentage rates. APR investment in monthly rate, and charge on credit card deposits times the monthly rate. Okay. Well, generally, if there are n compounding periods in a year, period is RFT, then the APR equals to n times RFT. Conversely, you can find the per period rate from APR as APR by n, equivalently T times APR. What the hell? Using this procedure, 6-month bond, 6-month rate of 2.7% is 2 times 2.7. 5.42 to generalize, note that for short-term investment, there are n equals to 1 by t compounding periods in a year. Sort of understood, not as good as the EAR one. Example 5.4, EAR versus APR. In table 5.1, we use 5.8 equation to find APR corresponding to an EAR of 5.8% with various compounding periods. Conversely, we find the values of EAR implied by an APR of 5.8%. Where is this example? Table 5.1. Okay, here it is. Annual percentage rates, APR, and effective annual rates, EAR. In the first set of columns, we hold the equivalent annual rate, EAR, fixed at 5.8%. Find APR for each voting period. In the second set of columns, we hold APR fixed at 5.8% and solve for EAR. Okay. Compounding period, T. What does T mean? I don't understand. Is T like the rate? No, it can't be the rate. T, maturity of T years. Okay, so it's gonna mature. Okay. Alright. Okay. Mature in 1 year. Huh. Okay. An RFT is the return, I'm assuming. I haven't stated it, so RFT and then API equals to 1 plus EAR about T minus 1 by T. So 1 plus EAR. EAR equals to 1 plus RFT. Okay. Continuous compounding. It is evident from table 5.1 that the difference between APR and EAR grows with the frequency of compounding. This raises the question, how far will these two rates diverge as the compounding frequency continues to grow? But put differently, what is the limit of 1 plus t times APR to the power 1 by t as t uh, gets even smaller? As t approaches 0, we effectively approach continuous compounding CC, and the relative and the relation of EAR to the APR denoted by RCC for continuously compounded case is given by the exponential function 1 plus EAR equals to exponential RCC equals to e to the power RCC, where e is approximately 2.71828. To find RCC, find the from the effective annual rate, we solve 5.9 for RCC as follows. Log 1 plus EAR equals to RCC, where ln is natural logarithmic function, the inverse of exponential. Both the exponential and logarithmic functions are available in Excel and called XP and respectively. Example 5.5, compounded continuously compounded rates. The continuously compounded annual percentage rate RCC that provides an ER of 5.8% is 5.638%. C table is 5.1. This is virtually the same as APR for daily compounding, but less frequent compounding. For example, semi-annually, the APR necessary to provide the same EAR is noticeably higher, 5.718%, with less frequent compounding. A higher APR is necessary to provide an equivalent effective return. While continuously compounding may at first seem to be a mathematical nuisance, working with such rates can sometimes simplify calculations of expected return and risk. For example, given a continuously compounded rate, a total return for any period t, RCCT, is simply exponential t times RCC. Uh, in other words, the total returns scale up in direct proportion to the time period t. This is far simpler than working with exponents that arise using discrete period compounding. As another example, look again at equation 5.1. There is a relationship between real interest rate R real, nominal interest rate R norm, and inflation rate I. R real equals to R norm minus I was only an approximation as demonstrated by equation 5.3. But if you expect all rates as continuously compounded, then equation 5.1 is exact. That is RCCR real equals to nominal minus ICC. Concept check 5.2. A bank offers two alternative interest schedules for saving account of $100,000 locked in for 3 years. Monthly rate of 1%, annually continuously compounded rate of 12%. Which alternative should you choose? Monthly rate of 1% will become 12%. Uh, I'll have to see the answer for this one, to be honest. So, what? Really? This was wrong? How's that possible? 1 plus. Huh. 11.24%. 13.3. Interesting. I don't know that. Very interesting. Okay. Anyways, the second one. We have the Sharpe ratio as well. Getting a little complicated now. Hell yeah, man. Okay. EAR equals to 1 plus 0.01. Okay, 0.01 is 1%. 1 plus rate to the power compounding number time t, 12 minus 1. Sure, okay. Huh. Hmm. Oh, wait, no, no, hold up. Hold up, hold up. Okay. Wait, what? By 12. I'm not understanding. Okay, you know what? Just fucking write it. We'll be alright. We'll be okay. 0.1268. Take your word for it. What else? So 12.68%. What about B? B is annually. So 3. Let's see what happens this time. Will it be 1 by 3? Oh, E. E is 0.12. How will that happen? 0.12 minus 1. Interesting. Okay. Pretty good stuff. I think I'm going to end it there. Nice 28-minute session. And yeah, it's getting a little complicated. Definitely. But interesting as well. I have done Fisher equation before my macro class, so that was fun to visit that again. And yeah, this APR and EAR stuff, really need to solve questions on it to really understand what's happening. But anyways, yeah, that was good. I'll do another one tomorrow and so on.